Good morning, guys. So, in our last class, we just started with the derivation. So, I'll again read the things about the circuit. What I have to do, I have to consider a transmission line. So, as you know, in the transmission line, one end I'll consider as a source, the other end I'm connecting it to a load. Now what next I have to do, I have to take a small part of this transmission line, two parallel lines you consider. I'll take that distance is from A to A dash. So when it is from A to A dash, what you can do is I will consider it this distance from A to A dash, let it be a very small distance, and I will denote it as delta z, because the direction what we are taking is along the z. We'll consider as for our reference. Now as I've taken that small part A to A bar, what are the components that we can see in that layer is, as I have mentioned, the distributed components you can see. One is a resistive property, so we are considering a resistance. Another, you will get an inductive property, so we are considering an inductor. Next I'll get your conductive property, so it is a conductance we'll consider. Next a capacitive, so we'll consider it as a capacitor. Why am I considering a capacitor? As you know, this acts like a two parallel plate, so whatever, when there is a medium, it will form like a capacitor, so it will have a capacitive, as well as the medium will allow the signal to travel. So what we are considering, there is a conductance, or that medium will have some amount of disturbance or something like that, or it will boost the signal to travel more. So we can consider it as a conductance. So how can I mention the names over here? So I will consider the names as, this is a resistance, I will consider it as R of delta Z, because we are considering it for that particular distance. It is not an actual resistor present over there, so we are considering it as R delta Z. Now next, let this be L delta Z, and this as G delta Z, and this as C delta Z. So we have defined, or we have named our components. Next what we'll do is, I'll consider about the voltages. This is a parallel, it looks like a parallel circuit, so normally at each and every point we'll get the voltage as constant. Since I have told the components are distributed over here, what happens at this starting point, you will get the voltage as let it be V of Z comma T. Normally we consider the voltage as V of T, right? But here we are considering it as V of Z comma T, because the voltage is a function of distance also. And the other end, after it reaches a distance of delta Z, that means this distance, your voltage over here will change to V of Z plus delta Z comma T. So this is the new voltage that you are going to get over there. Now about the current, I can say, we'll consider the current, let the current be, I'll consider the current as current which is entering here, let it be I of Z comma T, and the current that is leaving this point, let it be I of Z plus delta Z comma T. So this A dash will consider somewhere over here, A dash, and this A will consider it is over here. So this is what you will get when you see that circuit that in that small distance. Now I have to derive the general solution. So to start with the general solution, first what I have to do is, I have to apply KVL in this loop. I have to apply KVL in this loop. So I will apply KVL in this loop. To apply, when I apply KVL over here, I'll start with the derivation now. So the KVL expression, when you consider, you will get it as what we have. we have voltage V z comma t and two components over here, and here the voltage is V z plus delta z comma t. So I can write it as V of z comma t is equal to, what do I have? The voltage drop over here is considered as R delta z into I of z comma t, right? Plus, next what do I have? L. So it is L delta z. What is that inductance expression you have? That is in terms of dou I of z comma t divided by dou t. This expression you know as you have studied in your smaller semesters. Next, it is the voltage drop over here. It is, we have already defined it in terms of voltage itself, so I need not consider the conductance or the capacitance. What I can consider is V of z plus delta z comma t. Fine. So this is what we'll have got when I apply the KVL. Now, what next I have to do? Why partial fraction? Because it varies with respect to z as well as with respect to time. It's a function of both z and t, so I have considered it as a partial fraction, partial differentiation over here. Next, what I have to do, I have to simplify this. To simplify this, what we'll consider is, on the LHS it is the same what we have, V of z comma t, which is equal to, let this be as it is, R delta z I of z comma t, plus this is also as it is, L of delta z dou I of z comma t divided by dou t. Next it is plus. Now this can be simplified as V of z comma t. I'll explain you why I'm writing this equation. It's dou V of z comma t divided by dou z where did I stop now? Yeah, over here. So it is dou z into delta z. So this part I have written like this. That means the voltage at this particular point is nothing but the voltage starting from here. So voltage from here plus the change in the voltage when it traveled a distance of delta z. So the actual original voltage is V of z comma t plus the change in voltage with respect to distance z into that distance traveled. So this is what you can write this equation as. Fine. Yeah. Next, let's continue. Next, what I can do, the V of z comma t can be cancelled with this V of z comma t. So what you will get over here is only, it is R of delta z I of z comma t plus L of delta z dou I of z comma t by dou t plus dou V of z comma t divided by dou z into delta z. Delta z. Now, for simplification purpose, what we'll do is we'll divide this equation. Everywhere we have delta z, right? So I can neglect that delta z. What we'll do is we'll divide this equation with delta z, and wherever we have I of z comma t, will consider it as simply I, and wherever we have V of z comma t, will consider it as V. This is just for a simplification purpose because we want the equation to make simple, that's it. So by doing that, what will happen to our equation? This side we have 0, right, because I have cancelled that. So this equation I can say it is equal to, what remains over here is R of I, because the delta z cancels with the delta z which I am dividing here, and I of z comma t will be replaced by I. So plus what remains over here is L of dou I by dou t plus what next is dou V by dou z, dou V by dou z. Now what we'll do is I'll take this dou V to the other side, so I can consider it as dou V by dou z minus dou V by dou z is equal to R I plus L dou I by dou t. So this I will consider it as equation 1. This I'll consider it as equation 1. So this we have considered it as equation 1. What next we'll do is we'll apply KVL. We'll apply KVL at this point. So when I'm applying KVL at this point, what all the currents that we can say? The current that is entering is one is I z comma t, which are the currents that are leaving over here. One is the current that is leaving is I, this current. The other currents are the current that is going through the conductors as well as through the capacitance, right? So what I can, the current entering is only I z comma t. The currents leaving are through G delta z as well as C delta z, and this is the third current. So the equation, by applying KCL, we can write it as I of, what is it over here? Yeah, it's I of z comma t is equal to G of G delta z. Oh, when it is conductance, I want current, so it should be a product of G and voltage, right? So it is V of, what is the voltage across that point? It is Z plus delta Z comma T plus C delta Z dou V by dou T of Z plus delta Z, because the voltage at that point is Z plus delta Z comma T, plus I of Z plus delta Z comma T. Fine, this is the voltage or the current when you apply the KCL that you are going to get. What next we have to do is, as I have done the simplification over here by where you had got V of Z plus delta Z comma T, which I had simplified, or we had distributed it as V of Z comma T plus dou V of Z comma T by dou Z. The same simplification you should apply for wherever the voltage is in this form and current is in this form. So when you apply that and when you simplify, you will be getting an expression. That derivation part, whatever steps I had followed previously, the same steps you have to follow, and you have to tell me what equation you are going to get. The equation looks similar to the previous this equation, and the equation will be, I'll simply write the equation. I want you guys to simplify that. It will be dou minus dou I by dou Z is equal to, it is G of V, GV plus C dou V by dou t. So this is the equation. After simplification you will get, it's a similar equation, just see the difference. In place of V I have I, and in place of I we have V, and in place of R it is G, and in place of L it is C. That is the only difference. But the simplification steps I have not done. I want you guys to complete it. Fine. Next, before going to our next step, what I'll do is we'll define what is V of Z comma T. Till now we just told it is V of Z comma T. We didn't say what is V of Z comma T. It is our voltage or current equation. As you know, in a polar form, you represent your V of T as, you normally consider U of T as what? A amplitude e to the power j omega t, right? This expression is a common expression which we had used till now in our previous subjects as well. So here it has a Z term also. So we consider that amplitude as V of Z, which is a function of Z also, e to the power j omega t, as well as I of Z comma t is equal to I of Z e to the power j omega t. This is what we have to assume, or we have to consider. Anything considering. Yeah. Next, what do I want? I have to use this v of z comma t and I of z comma t in my above equations 1 and 2 for simplification purpose. So how to use them? What we can do here is, we know that what v of z comma t I have taken previously, we have told it is nothing but our v, right? So in my equation number 1 v, in this place I have to substitute this. So what happens to my equation now? It becomes substituting, if you want you just name this as 3 and 4. As for your simplification, we can say equation 3 and substitute 3 and 4 in 1 and 2. 1 and 2. Yeah. So when you substitute that in 1 and 2, what happens? I'll do it for 1. For 2, you have to do it by your own. So minus dou, what was the equation? Dou v by dou z. So dou v is v of z e to the power j omega t divided by dou z. You have the equation 1 is equal to what was that? R of I. What is I now? It is I of z e to the power j omega t plus what next? It is L of dou I by dou t. So dou by dou t, I is nothing but I of z e to the power j omega t. Now what I have to do? I have to simplify this. How can I simplify this? Now everywhere there is e to the power j omega t term, but directly we can't neglect this e to the power j. I can't cancel this e to the power j term because here it is a function of t, right? So what I will do, in my next step I will, let us integrate this. So when we differentiate this, so when we differentiate I of z e to the power j omega t as it is plus L, it is dou I by dou t. I of z acts like a constant because the variable is t over here. Now this becomes e to the power j omega t as it is into j omega. So this is what you will get. On the other side it is dou v of z divided by dou z e to the power j omega t. Next what I can do is, we can cancel e to the power j omega t terms everywhere. Now this is not a function here we consider it. So we can cancel. What remains is minus dou v of z divided by dou z is equal to, it's R I of z plus L j omega into I of z. This is what we will get. I can take this I of z here common outside. So what I can write is, it is R plus j omega L into, it is I of z. Now whatever that v of z and I of z we have, we consider it as simply capital V and capital I. So I can write this expression as minus dou v by dou z is equal to z into I, where z is nothing but R plus j omega L. This we have seen in our EEM, which is nothing but impedance. This is nothing but impedance. Now, so we got one expression over here. Now, in a similar way, similarly, I will go where did we stop? 3 and 4. So I'll consider this as equation number 5. Now if I simplify my equation number 2 with the same procedure, I should end with an expression minus dou I by dou z is equal to y into z, where you will get a term. You have to tell me what is y. What is y? Fine, that is kind of, it's like a task for you guys. I'll tell you, so you have to complete it. Next, now what I have to do is, I have to find out over here, I have to consider what are the roots over here. I have to consider what exactly my differentiation should taken as, since my equation has voltage since my equation has voltage and current in the same equation, I can't simplify this. So since I can't simplify this, what I have to do, I have to make it as a single equation, or in terms of either voltage or in terms of current. So for that, what I have to do is I have to differentiate this expression once again with dou z, with z. So sixth, I'll consider differentiating equation 5 with respect to z. So what happens now? This equation becomes minus dou square v divided by dou z square is equal to, what do I get here? It is z acts like a constant. Don't get confused with this z and this z. This z tells you about the impedance, and this is a small z we are considering, which is our distance. It is z of dou I by dou z. Fine. Now what is our dou I by dou z? We know that dou I by dou z is this, right? Yes. So what happens to our expression? This becomes z. What is dou I by dou z? It is minus by v. Fine, capital V. So this, upon further simplification, rearranging, it becomes minus z by v. Fine. Now what we can do here, I can write it as minus dou square v divided by dou z square is equal to minus z by v. Our ultimate, I can say our final aim is to find the expression for voltage as well as the current. So this is what we will get here. Now from this, what I can say, I can neglect this. This becomes positive, so what remains is dou square v by dou z square is equal to z by v. Now this z into y, I will consider it as gamma square into v. Fine. Now in a similar way as I have done here, what did I do? I had differentiated equation 5 with respect to z, right? In a similar way, if you do with respect to equation number 6, if you differentiate with respect to equation number 6, what you will get is, you will get the expression dou square, I guess now you can imagine, dou square I by dou z square will be equal to gamma square into I. The whatever, in place of voltage, it will be in terms of current. Now I'll consider this as equation 8. Fine. What next I have to do? Now I have to solve this second order differential equation. To solve this second order differential equation, now consider equation 7. By considering equation 7, what I can write? How will you solve the differential equation? You have already studied in maths. So what, this partial differentiation or the normal differentiation, you have to consider it as d square, right? It will be equal to d square is equal to gamma square. Now this can be written as d square minus gamma square is equal to 0. This is the equation you will get. It is a second order. So the solution for this, either d will be equal to plus or minus gamma, right? So this is the solution that you are going to get. Now what is this gamma? Gamma is called as a propagation constant, which is equal to, gamma square was z into y, right? So gamma will be is equal to square root of z into y. When it is square root of z into y, what I have can say, it is equal to alpha plus j beta. It's equal to alpha plus j beta. So now I have to write it in my solution as a solution. So what I can consider, I was solving for v, or I can say it was for v of z. So v of z is equal to, what is it? It is, normally how will you write the solution? A constant into e to the power any one root plus c2 the second constant e to the power gamma z as my next root. It is plus, one is minus, the other one is plus. That is what I have considered over here. Now what I can do from this, it is gamma, sorry, now I have to say what is that C1 and C2. We'll consider C1 as V plus e to the power minus gamma z, and C2 as V minus e to the power gamma z. I will tell you why I have taken V plus and V minus over here. I'll explain that later. Now in a similar way, I can write for my I of z. When you simplify in the same manner for the current expression, you will get it as I plus e to the power minus gamma z plus I minus e to the power gamma z. Why this equation? Why it is I plus and I minus, and why it is V plus and V minus, we'll say it later.